My series will be longer than 2 hours. Okay, I set myself 2 hours limits. Now it's already more than, Anyway, so this video, the purpose of this video is actually to clarify all the doubts that I've made, and also some explanation that have caused any unnecessary misunderstanding. So in order to solve all these things, to make sure you fully understand, I'll do this video. So before we start, we need to before we start going into the vector polygon, we need to clarify. So yeah, previously we were talking about solving x equals to complementary function plus particular integral, right? And then we say that it is under them. Okay, so the whole understanding over here, it's right. Okay, it is correct. Okay, because we are talking about this portion over here, there will be a certain oscillation, and therefore definitely there will be certain underdamped system. Okay, there will be certain underdamped occur. So therefore we can actually use this. Okay, so nonetheless, if you were to take in the opposite way, it will eventually decay, right? But however, it starts from decay and eventually, so we can still use the same equation. However, we are talking about steady state. Okay, we are talking about steady state. We are looking for, if you remember the very analogy of the setup of the chop. Okay, if you were to, just starting, you wouldn't want to let the machine start to put the item inside here. So before you put the item, you have to let it, oscillate until it is steady, and then we can put in the item over here, and then you can, and then 1 second, 2 second, 3 second, and then the first second it chop, the second second when it goes up. Okay, then so for the for that third second this one will chop the next item, right? So within 1 second you have to switch away the old item, and then you bring in the new item, and then for the third second you chop, and then fourth second you come out, fifth second you chop the new item, sixth second come out, seventh second you chop the new item. So with this concept, we actually, so therefore you need to set this system into a steady state first before you can let it, work. Okay, let it produce necessary work. Then you want to design for it to work, right? Definitely you want it to be steady state. So therefore, when talking about steady state, there will be no damping factor, right? Because it is, as we say, it is the amplitude is all about the same, frequency is all the same. So all in all, it's about the particular integral. So I want to clearly make sure you know that if you are talking about this portion over here, if you are talking about this damping factor over here, okay, then you need to have this plus the particular integral that you have. Okay, so the particular integral, I'll just let me show you. Okay, it is actually this equation over here. Okay, not in this equation, but hold on. Okay, never mind. So the particular integral you have to solve it yourself. Okay, which later will which we are still doing it. Okay, we are still doing this particular integral. Okay, but if you're gonna solve this portion over here, you're gonna use this one. Okay, plus this one. But nonetheless, I don't think they will ask you to solve this portion, but rather than this portion over here. So if let's say they want you to solve this portion, my intuition tells me that you have to have this plus this. Okay, not just only this one, I think. Okay, so with these, I hope I can give you a very clear understanding. So just to um, you know um, you know yeah. So particular integral only applies for a steady state. So for steady state, only particular integral is used to determine the amount of amplitude, which is this point. Okay, yeah, whatever amplitude we are talking about. Okay, so with this, let's go to here. Okay, uh, hold on a while. Okay, so we also talk about the trial function. Okay, the particular integral trial function, if you remember, where before we differentiate, okay, we differentiate 2 times and then we sub that into this equation, right? So we explain this part. Okay, I may be wrong, but the proportional wise is okay. Okay, I mean it makes sense that the amplitude itself is proportional to the forces applied. Okay, because it's related to the amount of distance moved also. So this portion I'm not gonna go through, but rather than I'm gonna go through this portion over here. What is this actually? Okay, so from the from your notes, okay, from your notes, chapter 4, it actually says that the phi, okay, the angle phi is with the displacement is the displacement vector lagging the force vector by an angle of phi. So it means that the displacement is lagging behind the force. So what does this mean? Okay, let's go back to my graph. So imagine the blue color one. Okay, this blue color line is the forcing function, which is the machinery that is pulling my, okay, hold on a minute. The forcing function that is pulling my mass down, right? This is the force of the input. Okay, so you have a certain force. However, um, the distance move, okay, the distance move, okay, x, okay, can maybe delay by a few seconds. Okay, I mean not few seconds, but a few milliseconds or whatsoever. Okay, so instead of like, because if there's no resistance at all, okay, if there's no resistance, air resistance or whatever resistance, it will the move it will move with accordance to the force itself. However, there is some unknown forces, maybe some friction, air resistance whatsoever. The displacement rate is much slightly slower than the amount of forces. You know what I mean? So if you were to go back to the to go back to control, okay, the amount of input power is equals to the amount of output, right? So the amount of input power is partially is given to giving a change to the system. Okay, the input power give a change. So in our case, the input power give a change to the to the distance x move, right? It give a change in the system. Okay, it give a change. Stock energy is some term to describe maybe the distance or whatever is okay one, but it's a measurement of the amount of things inside. So maybe some height, maybe some x or whatever. But nonetheless, plus power losses. So power losses may be some unknown. So as you know, input power can be associated with these things in the output. So this is why if you use this concept and head back to our explanation on this, you can see that yes, indeed, the displacement of the x itself may lag behind the forcing function because of some unknown air resistance. So therefore, we are lagging behind by phi, okay, by phi, by this angle phi. So this equation, I mean this portion over here relates to relation between forcing function and the displacement. Okay, so it's the function and the displacement itself. Okay, so I hope that I can make this clear. So although the function may be fast, but the movement itself has certain restriction. Okay, the movement of the mass, so therefore does not move with the same speed as the driver. So with this, I hope I can let you understand. And nonetheless, I still got one more, so hold on. The next thing is to why we change sine to cosine. Okay, if you remember, just now, I mean previously we talked about why this is a very hairy formula, right? We do a lot of stuff. Okay, we derive up to here. Okay, this is a particular integral, and then we choose this one, and then we just explain why we actually choose this one. We explain the phi, and then after that we differentiate two times, you just sub in back into this equation, and then you got a very hairy formula. Okay, and then you rearrange a few stuff, and then you get this one, and then we say that okay, everything is cosine and this is sine. Okay, why the reason why we change this to sine to cosine is because everything here is cosine. Okay, everything is cosine. So you can only the simplest inefficient way is to just change the sine to cosine and that's it. Okay, but this is one of the objectives. But however, the true purpose of this is actually to make sure everything is in terms of the same cosine. I mean in terms of the same, same variable, I would say. Okay, so what I mean. So if you were to head back to this page over here, it is similarly like ax plus bx plus cx. Okay, so if you say sine beta, then this one will be like by. If it's like, so you have some y over here already. Okay, so which is like two variables, and apparently since you can attain in terms of one variable, why not? Okay, and with this concept, you can also see that we are we are talking about 1D. Okay, we are talking about one-dimensional analysis. Okay, so far we are talking all about the math system. Yeah, may I show you the picture? Talking about the math system, and then only the distance is moving. So this is just the x itself only. Okay, so but don't complicate my x with this term x. Okay, don't complicate yourself with my x, which is over here. Sorry, which is over here. This x is simply saying that it's the x-axis. That's all. Okay, but this x can be also used in terms of this thing. That's don't want to complicate you much. But the concept is there. Okay, the concept is there. So why do we, so you finally understand why this is it. And another analogy is that if you were to plot it in terms of vector polygon, so this I'll take this as an opportunity to introduce you to vector polygon. Okay, so imagine you have a cosine theta plus b cosine blah blah, okay, blah blah blah, and imagine you want to draw this thing. So this is a, and then a cosine is just this portion over here. So what if your b is in this direction? Okay, if your b is in this direction, then your b cosine theta will be some values. Okay, it should be, okay, so hold a while. So it should be b cosine beta. Okay, b cosine beta, some beta angle. So and then c cosine phi. Okay, so in this direction. So if you were to plot them, so this is a cosine and b cosine b, green color, okay, this, and then c cosine this one. So if you were to plot in terms of cosine, in terms of the x phenomenon, you can see that eventually the path you are going around back. So your displacement eventually is just moving this small distance over here only, right? You go one round and then you come back here. So you can easily analyze certain things in terms of one dimension. Or however, if you were to introduce, like, let's say sine, hold on, I write using my pen. So let's say sine cosine beta. I mean, sorry, what sine? Sine b sine beta. Okay, you're talking about this one over here, right? And then if you will talk about c sine phi, and then you move in this direction. Then this is sine, and this is cosine. And then what the hell you are talking about? You have to also translate this thing into here. So imagine you see there is a big differences. You are going two different ways already if you use sine. So this one is totally, so I hope you get what I mean, why we actually change everything to cosine, because eventually you want it to be in the same dimension, okay, same x dimension, y dimension, and then you just do this, and then you analyze. So eventually, if you were to have, let's say you have like so as you can see, if you introduce a new system d cosine alpha, okay, d cosine alpha over here, and then this angle is going in this direction, you eventually has a closed loop system. Okay, close up the system, taking that the angle is nice, everything comes in this manner. You have a polygon. Okay, so this is what it is. Sorry, in terms of the thing. So in terms of our vector polygon, so as you can see, this is the key understanding. So what I have so far thought about the concept of complementary and particular integral. When do you use complementary function, and why do we always use particular integral? And then we analyze why we have a lag in the phi angle. What is it about? and then we talk about why we change sine to cosine, and then what is the reason, the true reason behind vector polygon, and then we are talking about 1D. So far we talked about 1D, free vibration. So we have talked about free vibration, then free vibration, and forced vibration, all about 1D in terms of the X itself. So it's a simple system, but eventually in the later of the sem we will talk about 2D. Okay, so I hope I understand this. And just to recap back, okay, we are still we are we are at the portion of particular integral. Okay, so where we stop is actually here. Sorry, it's actually here. Okay, we have a very hairy formula. As you can see, we're having cosine, 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 and this cosine of here. It is the same analogy to my ax plus bx plus cx plus dx. Okay, same thing, you know. So with this, we'll do next video we'll do about vector polygon, and eventually we'll solve for the x. Okay, so I'll see you in the next video.